Everyone, in this session I'm going to explain you all about demultiplexer. What is a demultiplexer? It basically reverses the multiplexing operation. What does a multiplexer do? It converts many to one. So the reversal of it is converting one to many. Obviously, a demultiplexer takes data from one line and distributes them to a given number of output lines. For this reason, we are calling demultiplexers as data distributors. Let us consider that we are going to have n data output lines. For that, we need m select lines. Then the relationship between m and n can be expressed by using the expression 2 to the power of m is equal to n, where you should remember n is the number of output lines and m is the number of select lines. Yes. Let us move on to the block diagram of a demultiplexer. What are the components of a block diagram? We should have a data input line and we can use the select lines as required, and the condition is it should be lesser than the number of output lines and output lines. Look at this block diagram. It has got a data input and m number of select lines which gives n output signal. So this is actually depicting the data distribution. So depending upon the select line and the data input, I can choose any of the output from this setup. Going into the different types of multiplexers, we should find out what is the difference between a demultiplexer and a decoder. Demultiplexer is a combinational circuit which accepts only one input and directs it to one of the several outputs, whereas a decoder is a combinational circuit which can accept many inputs and generate the decoded output. Our first example is 1 to 2 demultiplexer. 1 is the data input and 2 is the number of output lines. See, this is actually the block diagram for 1 to 2 demultiplexer. Here is the data input and we are giving one select line which gives us two outputs. This is actually the logic diagram. You can look at the truth table where the truth table has select line and input D, which is giving outputs Y0 and Y1. We have an enable input which is used to control this demultiplexer. This enable has a significance. When its value is 0, the demultiplexer will not operate. Whereas if the enable is high, then the demultiplexer will operate. Depending upon the data input given, it will be connected or it will give the output. From the truth table, if both the select line and the input are low, that is 0, we cannot find any output lines connected. Whereas when the enable is high and the select data input is high, we can get the output Y0. Similarly, when the select lines are 1 and the data inputs are 0 and 1, the outputs are recorded accordingly. Look at this. When select is high and data input is high, Y1 is connected. So this is actually the logic diagram for 1 to 2 demultiplexer. Look at this. Enable line is connected to both the outputs, and one main thing is we are using only AND gates to draw the output. So this is the select line and this is the single input data line. So depending upon the truth table, the min terms can be obtained. What are the outputs? Y0 and Y1. Next, we are going to move on to 1 to 4 demultiplexer. Look at the block diagram. The input is 1 and the outputs expected are 4. We know the relationship n is equal to 2 to the power of m. So 2 to the power of 2 comes to 4. So the number of select lines we are going to use is 2. Obviously, the enable is missing here. So we all know when enable is 0, the demultiplexer will not work. When enable is high, the demultiplexer will be working. Right. So you can look at the truth table. When enable is 0 and the rest of the data line as well as the select line, we are taking it as don't care condition. Irrespective of the value of the data line and select line, if enable is 0, there are no outputs in the demultiplexer. So when the enable is high, irrespective of the data input which we are going to give, if the select lines varies from 0, 0 to 1, 1, we have listed the outputs of a demultiplexer. Our main aim is to connect this input line to any of the outputs. So depending upon the select lines, we are going to get connected to the outputs. So when is Y not connected? When is Y not getting connected? When the select lines are 0, 0 and the data input is either 0 or 1, provided the enable is high, the output line Y0 is connected, which is represented by D, and you can easily remember that you should draw an AND gate for representing the output. D symbolizes an AND gate. This is just a hint. So accordingly, when enable is high, data input is X and the select line is 0, 1, Y1 is connected, or we are going to get the output at Y1. Similarly, these two cases. So D takes AX and 1, 0 for select lines, we get the output line Y2 is connected. So for data input X, select lines 1 and 1, we have output line connected to Y3. So this is actually the procedure behind 1:4 demultiplexer. Yeah. Next comes our 1:8 demultiplexer. Now the enable is not actually shown, it is obviously understood, right? What is the data input here? The data input is not going to change anyway, only the number of output lines that we are going to connect is changing. Distribution of lines is changing. So 1 is the input and the output that I require is 8. 8 means 2 to the power of 3. 2 to the power of 3 in the sense 2 to the power of m. M is equal to 3. So we are choosing 3 select lines and the outputs are 8 lines. Moving on to the logic diagram. Hope you can understand the logic diagram now. So D is the data input and you assume there is an enable at high connected to all the AND gates. So there are 3 select lines. Depending upon the select line, we are going to have the output lines. So this is actually the truth table for 1:8 demultiplexer. Like how I explained for 1:4 demultiplexer, we have the same operation here also. When enable is low and data input as well as the select lines, irrespective of whether it is 1 or 0, there will not be any output lines connected as such in the output. Whereas when enable is 1 and since we have 3 select lines, obviously you know the combinations moves from 0, 0, 0 to 1, 1, 1. So if enable is high and the data input is either 0 or 1, depending upon the select lines, we have Y0, Y1, Y2, Y3, Y4, Y5, Y6 and Y7 enabled as such to get the output. So we would have seen a similar example while designing a decoder. The actual aim for us is to design a 1:8 demultiplexer using two 1:4 demultiplexer. How can we design that? We can combine two 1:1, 1:4 demultiplexer like this. What are the select lines, or how many select lines we need? We need two select lines. We already know that we are supposed to give an enable input. If the enable input is 0, we can consider 4 outputs, that is from 0 to 3. Having enable as high, we can connect it to find to 4 more lines. So what are the inputs that we are what is the data input here? Data input is here, an enable line, and B and C are the select lines. So with the enable 0, we can have 4 output lines, that is starting from Y0 to Y3, whereas for a high input enable line, we can have 4 more data line, 4 more output lines connected, that is 4, 5, 6 and 7. This is how we design a 1:8 demultiplexer. Hope you would have understood what is a demultiplexer. Thank you for listening.